So, I will take up another example. Design a steel beam section for supporting a roof of a hall for the following data and apply usual checks. Take Fe410 grade steel, clear span of the beam equal to 6.5 meters, end bearings equal to 150 mm, center to center spacing of the beams equal to 3 meters, imposed load equal to 10 kN per meter square, dead load including self weight equal to 4 kN per meter square, restriction on the beam depth equal to 375 millimeters. The compression flange is laterally supported throughout. So, the compression flange is laterally supported, so we have to design laterally supported beam for the for this given data. So, beams, as beams are spaced, as beams are spaced 3 meters center to center, the loading of slab, the loading of 3 meter span of slab will be acting on the beam, So, the UDL dead load equal to 4 kN per meter square, lie load equal to 10 kN per meter square. Total load is equal to dead load plus lie load. It is 4 plus 10, 14 kN per meter square. 14 kN per meter square. Then UDL per meter run. UDL per meter run on beam is equal to 14 into 3, 42 into 42 kilonewton per meter. 14 into 3, 42 kN per meter. Then factored load equal to 42 into the load factor 1.5. This is equal to 63 kilonewton per meter. So, 63 kilonewton per meter is the load. It is the factored load which will be acting on the span of the beam 6.5 meters. So, the effective span of beam equal to clear span 6.5 meters plus the width of the bearing at this ends, it is a 0.15 meters. So, it is equal to 6.65 meters. Effective span of the beam equal to 6.65 meters. So, the maximum bending moment M max equal to WL square by 8, 63 into 6.65 square divided by 8. So, this value will be 348.25 kilonewton meter. The maximum shear force at support equal to V equal to, it is WL by 2. So, W is 63, L is 6.65 divided by 2. So, V equal to 209.475 kilonewton. So, the maximum shear force acting on the beam equal to 209.475 kilonewton. Then ZP required, plastic section modulus. ZP equal to plastic section modulus. Required, it is equal to M divided by Fy into gamma MO. So, maximum bending moment is 348.25 into 10 power 6 Newton mm divided by Fy is 250 Newton per mm square. Gamma MO is 1.1. So, the ZP required, plastic section modulus required, is equal to 1532 0.3 into 10 power 3 millimeter cube. So the plastic section modulus required for the beam to be selected is 1532.3 into 10 power 3 millimeter cube. But the depth of the beam is restricted to 375 mm. Depth of beam is restricted to 375 millimeters. Therefore, try ISWB 350 at 558.19 Newton per meter. ZP of the beam is equal to 995.49 into 10 power 3 millimeter cube. But the ZP required for the beam section is 1532.3 into 10 power 3 millimeter cube. So it is more than the ZP of the beam. Therefore, we have to provide the cover plates to the flanges of the beam. So ZP required for the plates, for the cover plates, equal to 1532.3 minus 995.49 into 10 power 3. This is equal to 536.81 into 10 power 3 millimeter cube. Now, this is the ZP required for the plates. Then area of the plate, area of the cover plate is given by ZP divided by H. So 536.81 into 10 power 3 divided by H, that is the depth of the section is 350. Hence, area of the plate required will be 1533.74 millimeter square. Keeping the width of the plate equal to width of the plate as width of flange of beam, that is 200 mm. Thickness of the plate required, it's equal to area of the cover plates 1533.74 divided by width of the plate equal to 200 mm. So it is equal to 7.668 millimeters. The thickness of the plate should not be less than 6 mm. The thickness of the cover plate should not be less than 6 mm, and therefore provide 8 mm thick cover plates on compression and tension flange. Of beam. Compression and tension flange of the beam. So there are total depth of beam equal to 350 mm plus cover plate thickness at the top 8 mm and at the bottom 8 mm. So it is totally 366 millimeters is the depth of the beam section. Next, plastic section modulus ZP provided is equal to plastic section modulus of the I section is 995.49 into 10 power 3 plus plastic section modulus of the cover plates will be given by area of the plate 200 into lever arm. So 200 into 8 is the area of the plate multiplied by the lever arm is 350 plus 8. That is the distance between the center of the cover plates. So this is equal to the ZP provided. It is 1568.29 into 10 power 3 millimeter cube. So it is more than ZP required. ZP required. Therefore, okay. Therefore, the selected section is okay. Then the properties of section will be properties of I section. Properties of I section, that is a flange thickness equal to 11.4 mm, web thickness is equal to 8 mm, then flange width BF equal to 200 mm, then B equal to outstanding leg of the compression flange equal to it is a 200 by 2 equal to 100 mm, 100 millimeters. Depth of web equal to H minus 2 into H2. So H is 350 minus 2 into H2. 27.25 is H2. So D equal to it is a 295.5 millimeters. D equal to, that is the depth of the web. Then IZ, moment of inertia of the section is equal to it is 15521.7 into 10 power 4 millimeter raised to 4. ZE, elastic section modulus of the I section is 887 into 10 power 3 millimeter cube. So epsilon equal to the root of 250 divided by Fy, which is equal to 1. Then B by TF equal to 100 divided by TF is 11.4. So this ratio is equal to 8.77, which is less than 9.4 epsilon. Then D by TW is equal to 295.5 divided by TW is 8. So this is equal to 36.93, which is also less than 84 epsilon. Hence from page number 18 of IS 800, this section is plastic. This section is plastic section. And also D by TW is 36.93, which is less than 67 epsilon. The check for web buckling check for web buckling is not required. It is safe. It is safe. It is safe. Then check for shear. Check for shear. The design shear force or shear capacity of beam is given by, shear capacity of the beam is given by Fy divided by root 3 into gamma MO into area of the web H into TW. So Fy is 250 divided by root 3 into gamma MO is 1.1. H is the depth of the section 350 into web thickness is 8 mm. So this design shear carrying capacity of the beam is equal to 367.4 kilonewton, which is more than V, that is 209.4 kilonewton. Therefore, safe in shear. Section is safe in shear. Next, high or low shear. High or low shear. High or low shear. So 0.6 Vd is equal to 0.6 into 367.4. So this is equal to 220.4 kilonewton. So this is also more than V. Hence, the section is of low shear, and therefore bending strength of beam is given by, bending strength of the beam is given by MD equal to beta B ZP into Fy divided by gamma MO. So it is equal to beta B is equal to 1, ZP provided for the section is 1568.29 into 10 power 3 into 250 divided by 1.1, or this is equal to 356.43 into 10 power 6 Newton mm. It is more than the M maximum bending moment, M max, that is 348.25 kilonewton meter. Hence, safe in bending moment also. But MD should be less than 1.2 into ZE into Fy divided by gamma MO. So as per the codal provision, the design bending strength of the beam should be less than 1.2 into ZE into Fy divided by gamma MO. So this is equal to 1.2. Elastic section modulus. Elastic section modulus is 1408.55 into 10 power 3 into Fy is 250 divided by 1.1. So this is equal to 384.15 kilonewton meter. So this is more than 356.43 kilonewton meter. Therefore, okay. Section is safe in bending moment also. Now, we have to apply the check for deflection and a check for web crippling also. for the section. Now check for deflection will be check for deflection. Permissible deflection for simply supported beam, it is equal to span divided by 300. So it is equal to LE divided by 300. So 6.65 into 1000 divided by 300. So this is equal to, it is 22.17 millimeters. Then actual deflection will be delta A equal to 5 by 384 into WL4 divided by EI. So this is equal to 5 by 384 into W is the working load. So the working load is 42 Newton per mm into clear span 6500 millimeters raised to 4 divided by E. E is 2 into 10 raised to 5 Newton per mm square. Then I for the section is 25776.52 into 10 power 4 millimeter raised to 4. So this actual deflection due to the loading will be 18.93 mm. So this is less than delta permissible, therefore safe in deflection. Finally, we have to apply the check for web crippling of the beam section. Check for web crippling. So this web crippling occurs due to the stress concentration on the beam section, and it is given by check for web crippling. Check for web crippling. Assuming stiff bearing plate of 100 mm width, bearing strength or crippling strength, web crippling strength is equal to FW is equal to AE into FYW divided by gamma MO, where AE is effective area of the web, which is given by B plus N1 into TW. But N1 equal to, it is 2.5 into H2. So 2.5 into 27.25. So this is equal to 68.12 mm. Therefore, AE equal to, it is a B plus N1 into TW. So this is equal to 100 plus N1 is 68.12 into web thickness is 8. So web bearing strength FW is equal to AE 100 plus 68.12 into web thickness is 8 into FYW is 250 Newton per millimeter square, and gamma MO is 1.1 into 1.1. So this is equal to 305.68 into 10 power 3 newtons, or 305.68 kilonewton, which is more than V, that is 209.4 kilonewton. Hence, safe against web crippling. Safe against web crippling.